I'm going to talk about Stylo and Handifact. It's a work about modulating haptic perception through visualizations for posture training. So this is a cross-disciplinary project between HCI and neuroscientists. This has been done with my colleague Jonathan Tong in neuropsychology and Oscar Ariza in our group. So to get to it, human leisure and sports activities often depend on activities which require a carefully controlled posture, like sports like Tai Chi, martial arts, or dance. And these activities are normally supported by a coach. The coach would come and correct your posture if you have a wrong posture. The coach would come over and fix you to the correct location. So we are interested in supporting these activities using some interactive system. And our approach is to have a head-mounted display. The user is also wearing a haptic device on their forearm. And through the head-mounted display, they're seeing some visualizations which help them go to the correct position, so correct their errors. The related work draws from three different areas, haptics, visualization, and also visuo-haptic illusions. For a detailed review, please look at the paper. I'm only going to mention a few of them. So Spelmazan and his colleagues looked at lining the body with an array of tactors. And they did this for giving instructions to people who were doing sports. They explored the design space by giving some directions like lean left, lean right, fast, slow. And they found that you were able to give quite a diverse range of instructions with these tactors, but they haven't looked at correct positioning or correcting errors. Some people have looked at, Lopez and his colleagues, they looked at electromuscular stimulation. And this work can also be used, we believe, for correcting postures. So you could get a muscle stimulation that tells you, hey, you need to bring your arm closer. But the muscle stimulation thing requires you to place a number of pads at specific locations on your arm, which might not be appropriate for daily or casual use. In the visual domain, people have tried to give instructions to let you know how well you're doing. So they give you good or perfect to let you know, okay, you did well, but they don't let you know exactly how well you did. Some people have tried this, so if you notice here, they're giving some call-outs, annotations to say, hey, you need to raise your arm. Again, this might not be ideal for situations that require precision or for depth situations. Anderson and his colleagues have tried to address this depth issue by popping up a window. So if you notice here, the foot is on the wrong position, and if you need to make some motion on the depth axis, it's not really easy to understand how to do that. So they're popping out these external callouts so you can understand from a different angle. And we are also addressing this topic, but I'll return to that later. So Huang and his colleagues have looked at the egocentric approach. So not looking at mirrors, not looking at external monitors, devices. You're wearing a head-mounted display, and you're seeing your coach, the limbs of your coach. So here you're looking at the blue is the coach, and the red is the limb that is in the mistaken position. And the correct position is obviously green, and you can use this egocentric system to bring your limb to the correct position. We're using this as a baseline for our study. This approach is also quite good. It's not exactly clear how well this would perform for minor corrections. So from the visuo-haptics illusion domain, we have Soft AR by Pung Pong Sanon. What they did was they manipulated the appearance of a pillow to make participants feel like it's harder or it's softer. So they have successfully shown that if you manipulate the visuals, you can make the participants feel like it's actually harder or softer, but nobody has looked at the reverse. So nobody has looked how visuals can affect a haptic sensation that is received on your body passively. You're not actively doing something, you're receiving passively some haptic response. So what we're trying is we are using the HoloLens to project on top of the forearm this visualization. The haptic device, we call it Stylo. And the visualization and the haptic device come together as a pair, and they supposedly complement each other to achieve the posture corrections. So I'm going to talk about Stylo first. Stylo is this device that you see here. It consists of two straps, the distal strap and the proximal strap. And this is anchored on the ulnar styloid process. So it's this lump here you have on your wrist. And the device anchors there, and it uses that as a point to nudge your arm. And the design of the device means that when you have stimulus that is being actuated here with this lever, the body of the device transfers the pulse to the rear strap, and you're getting some sort of wave-like sensation which is ambiguous. So in fact, this device has been designed to be ambiguous. Not only low in amplitude for your haptic sensation, but also kind of a sensation that you're not sure exactly what's going on. And we also attempted to induce the tactile, it's a neuroscience effect, cutaneous rabbit illusion it's called. And they say that when you actuate two taps on your body, when you receive two taps in close rapid succession, the tap feeling is going to feel like it's floating between the two straps. So we tried also to induce this thing using these two straps. Neuroscientists have this thing which is called Ventriloquist Effect. And they explain this effect using the causal inference model. So if you see here, we're supposed to be getting audio, but we're not getting audio. It's plugged in.
Silence! I kill you!
So this is ventriloquism. Why does ventriloquism work? So you have your two modalities, which is your auditory and your visual modality. And you're seeing, you're hearing, because the voice is coming from the ventriloquist's throat. So your visual system is giving some sort of reliability here. Your visual system thinks that, okay, the audio is coming from this direction with this certain of confidence, with this level of confidence. But because your vision is much more confident that the puppet's mouth is moving, so, and this actually works super additively. These two stimuli are super added to create a final estimate. So your brain estimates where does this stimulus is coming from. And because the visual dominates, you get this illusion working that the puppet is actually talking. And this is what we tried to take advantage of when we made our device somehow ambiguous. So we're hoping that the visuals, the haptics are low and ambiguous, and the visuals are more salient, so we're expecting there to be some sort of interplay between the senses. Inside the Stylo is just a normal motorized fader. And this is what the audio engineers have in their consoles. It moves automatically back and forth. And this lever here moves back and forth to actuate this strap, and through the body you get rear actuation. And this is the device firing. The noise is way too loud. It actually is not really that loud. So this fader is quite quick in moving back and forward. I will now talk about Handifact. Handifact is basically a visualization of an arm, and we're trying to address the problem of giving direction instructions for making any kind of motion, basically, movement. If you look here, if you want to show somebody that they need to move on the x-axis, you can show them with an arrow. And the same goes for the y-axis. The arrow is quite salient. But what happens on the z-axis? If you try to communicate this with an arrow, it's not easy to judge the magnitude of the arrow. So we are proposing the use of this rigged arm. So we basically just rigged the model of an arm. And we are assuming that the level of pressure kind of communicates the magnitude of the motion that you need to travel with. So we tried now to do a user study to answer the following questions. First of all, is it possible to induce a believable illusion? Can people think that this is actually a hand that is touching them? Does this pair work together well? The other question is, Because Stylo is a haptic device, it's an active device, it needs energy. We want to be able to give some sort of, be able to expand the range of haptic forces that Stylo is rendering. If we can expand the range, then we have savings in energy. And finally, we want to find the distance that this illusion breaks down. The question here is, how many of these devices do you need to strap on your body to get sort of a complete full body posture interaction, feedback? Do you need one, do you need two, and in what distances? This is what this third question is trying to answer. So we did this by running a control user study. 12 participants between 18 and 35 years old from the student and staff population of the university. Participants sat on a desk with their head on a chin rest. They were wearing Stylo on their non-dominant hand, and they had the HoloLens, and they wore noise-canceling headphones. So you see here we're using a drape so that we hide the lever moving. So we don't want participants to be able to judge the magnitude of the force by the movement of the lever. We just want them to feel the sensation. And participants in this experiment received 2 taps, and they had to compare and say which one was the strongest tap, and they answered using their hand here on the keyboard. So you can see here the haptic discrimination experiment. Participant is receiving 2 taps. And also there's a condition where Handifact is not rendered at all. You might not be able to see it, but the device is actually firing very slightly in the background. And participants need to choose which one of these 2 taps is the strongest. So we controlled a number of different conditions. One of the things that we controlled at this experiment was the level that the Handifact was pushing. And we had 3 different levels: a light animation. So Handifact made an animation. It was kind of a light touch, a medium touch, and a strong touch. And this one is anatomically incorrect on purpose. So we were expecting that this anatomically incorrect posture would trigger participants into thinking that was a huge force coming in on their arm. The other thing that we manipulated was the location of Handifact. So there was a condition where Handifact was right in between the 2 straps, which we call the no offset condition, and then it was offset to be rendered just outside the proximal strap, so just right here. That was the offset condition. In addition to this, we tried a range of forces. So the reference tap, the one that was fixed in every single trial, the one you needed to compare against, was 42 grams of strength. And that was always paired with the medium animation. So light, medium, strong, it's always the reference is 42 with medium. And the comparison tap that you received, which was randomized, of course, the order, ranged between these forces. So how do we come up with these forces? This is pretty much the lowest distinguishable range that Stylo can render in forces. And we did a pilot study, and we find which of these ranges are enough for people to distinguish without any visuals, without nothing. And participants did close to 1,000 trials of comparing each of these 2 pairs. So the results of this experiment. Before we understand the results, we need to understand how this psychometric fitting works. On the y-axis here, we have the proportion that participants judge that the comparison was stronger than the reference. If you remember, the reference was always fixed here on 42 grams. So, as you can imagine, if the comparison stimulus is very low in intensity, if it was on 30 grams, the percentage that people are going to say it's stronger is very, very low. And as we increase in intensity, things start to get ambiguous. Around 42 grams, you see that people are starting to be unsure, so they're pretty much guessing in this situation. And as the comparison increases in strength, people again start to be more confident as to what is happening. And the colors, the different colors here are each different animation that was paired with the nudge, but I won't explain this in the next slide. What you need to understand here, we do this curve fitting so that we can find here the point of subjective equality. And this point here is, if you see the next slide, This point tells you, here we have the strength on the y-axis now. This shows that when nudges were paired with the light animation, you needed to make them more than 43, like 43.5 grams, in order for them to feel the same as the reference. So these are all the values where people were performing at chance. So this shows that the light animation, in fact, made the stimuli feel lighter and feel softer in comparison to the reference. The strong animation was not very successful. We'll come back to this as to why this happened. And this is for the no offset positions. This is when Handifact is between the two straps. If we look at the offset condition, again, same procedure, fitting the curve and finding the point of subjective equality, we can see that here the effects are magnified for some reason. So the light animation was even more successful in making stimuli feeling lighter. And here we have even statistical significance with the strong animation. And even more surprising, when in the non-condition is when Handifact is not rendered at all, is not visible at all. People thought when Handifact was not visible that the stimulus feels stronger because their brain was primed to associate 42 grams with the medium animation. 42 grams of the medium animation. When they didn't receive the animation, the haptic touch felt like it was actually lighter when there was no animation. So the brain was somehow recalibrated. And this is, again, is the offset condition, where the Handifact was outside the device. Whether or not visuo-haptic integration worked, the majority of participants said that they really felt that the hand was touching them. So there was success in getting these things feeling realistic and integrated. How about why was the light animation more successful than the heavy? So we believe that because in the animations, here when you look at the animations from the side, it's quite salient to see the difference between the medium and the strong animation. It's quite visible, but participants saw them from a sort of different angle. So this means that the differences were not so apparent for them. So we believe that was one of the reasons why the strong animation was not so successful. Another finding, which was a big surprise, was that when Handifact was rendered outside the device, there was a stronger bias, and that came as a big surprise to us. One theory we have is that in general, people are better at localizing senses near anatomical landmarks. So near your wrist or near your elbow, you're much more sensitive in understanding taps. So when Handifact was projected, when in the offset condition, it was projected pretty much near the middle of the forearm. And there, participants' sensory system would expect this to be stronger. So immediately there was somehow a recalibration and made it feel somehow lighter. But we don't have any strong evidence. This is just a hypothesis. Next, we did a posture matching study. I'm running out of time, so I cannot really go into the details. People stood and wore stylo in their arm, and they had to match different wrist positions. So they started from a home position, and they had to match different positions, and they always returned to their home position to go to the next trial. We compared with one body, the baseline, and we implemented one body exactly as Huang and his colleagues, and we had also some different conditions, which is the one body as it was, vanilla from Huang, one body plus Handifact, which is the device firing in the beginning, the arm pushing in the beginning of the trial to guide you to the correct direction. One body plus stylo, which means you get a haptic sensation in the beginning of the trial, also in the 5 centimeter threshold, just like Huang and his colleagues. And finally, there was a condition with everything combined together. Of course, everything was counterbalanced. And you can see here, this is the one-body Handifact stylo, the condition where everything is working combined with everything. The hand is pushing you at the 5 centimeter threshold. The fingers are kind of relaxing their push, and also the one body becomes green. So the results from this study was that we got an approximately 5-second docking time here. So lower is better with one body vanilla. And then when you increase Handifact, you have an improvement of 0.8 seconds approximately. Then when you introduce Stylo, another improvement. But the surprise here was that the combined improvement of both of them was better than the sum of its parts. So the sum of its parts was 1.9 seconds, whereas we saw a better improvement. This means that there's some sort of visuo-haptic integration happening. And we also believe that some of these results come from the fact that the field of view is limited. You're wearing the HoloLens. So the Handifact is actually giving you an immediate clue to go to your destination. Limitations of this study, the noise of the device could be an issue. Reviewers actually asked about this. We didn't see any evidence of the noise giving you cues about the magnitude of the strength, even though the device does make some noise. The forces we measured the forces when the device was outside of the arm. So we measured the force that this lever is giving, but we're not exactly sure how forces are delivered when users are wearing this device. And we were not able to answer how integration breaks down when the stimulus moves further away, Handifact. And in fact, there was an amplification in that condition. So yeah, to conclude, Stylo felt congruent. It was able to modulate haptic perception by 5%, and there was some sort of visuo-haptic synergy that resulted in better performance in the docking task. As future work, we are interested in exploring visual attributes. There has been some work that shows that it's easier to understand the contour based on the luminance channel of photos, and also we're interested, okay, Handifact, Stylo can communicate pushing and pulling directions, but what about twisting the arm and turning the arm and doing all sorts of other corrections? So with that, I would be happy to answer any questions.
Let's thank Nicholas, please. Questions?
I lost the first few minutes, but probably I've used it in the past some small vibration engines, so just giving a vibration instead of hitting stimulus. Do you try this solution instead of this one?
So we are mentioning in the paper, actually, we avoided vibrating tactile arrays because they have been shown to be very, very, very accurate. So participants in studies with vibrating tactile arrays are able to even more than 90–95% accuracy. So if you have such high reliability, then maybe it wouldn't be able to integrate well with the visuals. So this is why we avoided this. We wanted something which was not accurate on purpose so that it integrates with the visuals from the HoloLens.
Okay, so just to say, looking at this hand, instead of using all the fingers, did you try to use the push of one finger to indicate a lighter push instead of the entire four fingers?
That is a good idea. In fact, we haven't explored this. The design space in visualization is very, very broad, and we haven't looked at it, but that's a good suggestion. Thank you very much.
Thanks. In the first video you showed, it seemed to go did, and then did I miss that? Like it didn't seem to be synchronized that the push and that the visual and the actuator were going at the same time.
In this one, you mean?
The very first one you showed with audio, it was like din, din.
That's a video problem. In fact, it was perfectly synchronized.
Okay, that's fine. That's no, first, I do have to apologize because I cut you short a few minutes. I made a mistake. So in the dinner, maybe you can finish the rest.
You can buy me dinner.
Yeah. No, yes, in the banquet. So one question. This is very interesting, but I was wondering, why did you select the 12 subjects? Why the number 12? Is it too long? Is it too uncomfortable?
So the study was quite long. Participants, they needed to stay on the chin rest fixed almost 1,000 trials.
Yeah.
So
yes.
How long was the experiment
Uh,
for subject?
Almost more than an hour, so
Wow, yeah.
sitting there in the chin rest is not easy. So.
Yeah, it's hard to get volunteers like that. Yeah. Yeah, this is very interesting. Is there any additional questions? All right. All right, let's then